Hello, everyone. Welcome. I'm Ellen Quinn. I'm the current QMD chair and your moderator for today. The title of this session is The Symbiotic Relationship of Measurement System Analysis and Process Capability. That's in the conference track Process Excellence. JD Marhevko is the speaker and the presenter. She is currently a president of quality for ZF Group's Electronics and ADAS division. Among JD's many accolades and awards, she's an ASQ Fellow, a Shannon Medalist, holds multiple ASQ certifications, and is a past ASQ QMD Chair, and currently is the lead for QMD's Strategic Planning CMC. She's also a very good friend of mine, and I'm really happy to be able to be here to moderate her session. A little housekeeping. The track session is for 45 minutes total. Q&A will be at the end of her presentation. Please enter any of your questions in the chat window, and depending on the number of questions, if we don't get to all of them, JD will have her contact information where you can reach her afterwards. Thank you, and over to you, JD.
Thank you, Ellen. I'm glad we were in sync on the background. That's pretty cool. We're both standing on the moon. My name is JD, and what we're going to do today is we're going to do a rapid, high-level overview about how process capability works. So please, if you don't have a paper and pen handy, because we are going to be interactive through this session, you're actually going to do a little bit so that helps with understanding. And then we'll talk briefly about measurement system analysis, MSA. We're not going to get into the actual calculations, but just how the two interrelate with each other so that we can see what it means to us as quality professionals. Well, let's talk first about the process capability ratio, either the CPK or the CP or PP. And it's the way the customer identifies if the process is giving us all good product, yes or no. And it's a ratio of the width of the specification to the process itself. So in this example, you see I have a spec of -10 to +10, and the width of that total specification is 20, 10 minus a -10. Then I want to be able to divide into it how fat my process is. So I've got all these little X's on the bottom. I've got about 20 readings that I've taken, and they've ranged from 2 to 8. So the average of all of those is 5. And I want to know how fat my overall process is. And what I can do is I can calculate how big that process is going to be by getting the standard deviation, which is 1.67, and I multiply that by 3. And my 1.67 times 3 is 5. And if I take that distance of 5 and I add it to the average, it gives me my right-hand process tail at 10. 5 plus 5 is 10. If I look to the left-hand side, I'm going to do the same thing. I'm going to take my average and I'm going to subtract 3 sigmas from it. And that's going to take me at 5 minus 5, which is 0. So now this is giving me the whole width of my process. My process is running from 0 to 10. And I want to know how many times that fits into the specs. Now, one thing to keep in mind is my biggest reading was an 8. And Sigma says, well, you're taking samples. And because you're taking samples, you haven't done everything in the process. Therefore, if you keep going, if you keep taking more samples, if you keep running this process, you will eventually get a 10. On the back end, the smallest reading I got was a 2. But if I keep taking my samples, Sigma says you're going to get a 0. So with that, we might want to make sure that we understand how many units are covered underneath my bell. I call the bell the bellbrella, the umbrella of the bell. 99.7% of our stuff is covered by that bell umbrella. 99.7. That's a lot of stuff. That's great. But if I'm making lots and lots of parts, if I have, for example, 1,000 units, that means 3 of the units out of every 1,000 are going to fall outside of that bell umbrella. I kind of look at them as roadies or groupies following a band. They're hanging on the outside fringes. They're always out there, and they're never covered underneath the bell. And we have to take care of those. So in this case, I'm going to have 3 parts outside of my bell distribution. 1.5 of them on the right-hand side, they're going to be outside of the bell and outside of the spec. But on the left-hand side, they'll still be outside of the bell. They're never covered, but they're within the spec because the lower spec is -10. So now let's look at what happens, excuse me. Sorry, this was for the full bell distribution. And this is for the CP looking at the whole process. And I can see that that fits in there fully 2 times. Now, when I look at my process capability, I'm looking at the whole spec width, which is 20. I'm dividing it by how fat my process is, which is 10. And I can see that that whole bell fits in there twice, 2 times. Now we look at, is the process centered? And that is it sitting on the 0 where the middle of the spec is at? In this case, it's not. So let's look at the CPK ratio, which takes that distance to the nearest spec limit. In this case, my average is at 5, and I'm going to my closest spec limit, which is the upper 10. And that distance is only 5 wide. 10 minus 5 is a distance of 5. And I'm going to divide into that. How many times does half of my bell fit in there, or 3 sigmas fit in there? And 5 divided by 5, it fits in there 1 time. If I want to look at this from the left-hand side, I'm going to take my average minus my lower spec limit, 5 minus a -10, which is a width of 15, and I'm still going to divide that by half of my bell, which is 3 sigmas, which is 5. And that fits in there once, twice, 3 times. So in this case, I have a lot more room for those extra parts to hang out on that left-hand side. But this is still showing me that on the right-hand side, with a process capability of 1, that I'm going to have non-conforming units. So what does this mean? How does this work for us? When I have my normal distribution, my normal bell, I've got those big, fat, thick spec lines, upper spec, lower spec. It doesn't matter what the spec is here. I've got 3 standard deviations going from the process from the middle to the right-hand side. In that plus or minus 1 standard deviation range, you can see I've got a 34.2%. Unknown caller. Put that on voicemail. I've got 68% in that plus or minus 1 standard deviation. That's more than half of your stuff, which is in that plus or minus 1 sigma range. In the plus or minus 2 sigma range, I'm adding another 13.6 on each side. So within plus or minus 2, I now have 95% of my results. That's a lot of my product. That's 95%. And if I'm looking at plus or minus 3 sigma, as we talked about, that's 99.7%. And we still have to worry about those 3 parts per thousand that are going to be hanging out on either side in this case. I'm going to have 1.5 or 0.15% on the right-hand side and 1.5, 0.15 on the left-hand side. So those parts are always going to be there. And this is a process capability of 1. The whole bell fits inside that spec width just 1 time. Now, keep your eye on where those thick black lines are, and we're going to make a process improvement, which means we're going to make the bell get skinnier. We're going to have a smaller sigma. Sigma is going to go on a diet. And now sigma has gone on a diet. It's skinnier, and I have changed 1 or more of 6 things in the process. Either my manpower, my machine, my material, method, measurement, or Mother Nature. One of those 6 things I've been able to adjust and affect to reduce variation and make my bell skinnier. The percentages are still in the same place. That plus or minus 1 range is still 68.4% of my stuff, but now it covers a smaller area. It's the same with the second, 95.6 for the plus or minus 2 standard deviations. And now you can see my third sigma is within. My spec lines are still out here. I'm still going to have that 1.5 outside either side of the process tails. Now in this case, they're going to be outside of the bell, but they're inside of the spec. And in this case, my process, that whole 6 sigma, it fits in there 1 1/3 times, one full-time with a third left over. So if I'm looking at my total range of my upper spec to lower spec, and it's plus or minus 4, and my sigmas are at plus or minus 3, 4 divided by 3 is 1 1/3. And that is where we really want to be for our long-term processes, for long-term running, because those little groupies, those little 1.5 parts on either side, they typically, usually, generally hang out in that fourth sigma pocket. That's where they like to hang. Let's look at the next level. Again, those upper spec limits, those spec limits are going to be staying in the same place. We're going to put in another process improvement, tighten up that bell. And now you can see how this, because the sigma's getting smaller, those ranges are getting narrower. My 68.4% are still within plus or minus 1 sigma. 95.6 is still within plus or minus 2. And you can still see those 1.5 hanging out either side of the tails of the bell, and they're hanging out in that fourth sigma. But now you've got a little bit more wriggle room. You've got more breathing space. Now here, if my spec is within that plus or minus 5 range, my whole bell is covering 6 sigmas plus or minus 3 on either side. And with that happening, that's a 1.67 range. 1 2/3 is how often that bell will fit inside of those ranges. So with that said, I want to make sure that we want to make sure that we're centered if we can be. But if you can't be centered, you've got a little room for your bell to shift either to the right or to shift to the left. So this is the last time we're going to look at this process. And now I've got my big fat spec lines are still in the same spot. My bell is super, super skinny because it's gone on a hyper diet. And again, you can see the plus or minus 1 sigma is still 68.4, and plus or minus 2 is still 95.6, and we keep going down. Now with this case, what's happening is I have room from the average, or from the middle of the process. I have 6 sigmas worth of room from the average to the spec line. And this is what we call 6 sigma quality. My whole bell can fit in there 2 times. I've got 6 sigmas on the right side. I got 6 sigmas on the left side, a total of 12 of space. And that bell fits in there twice. And that allows me to have 6 sigma quality. Those parts, those groupies are still going to be up there. They're still going to be hanging in that 4th sigma range generally. And that only works if your process is normally distributed and has a bell. So what happens is when we start a process, and I always have to say this very carefully, shift happens. And with that, with our initial process in the top right-hand corner you see there, if I start my distribution in the middle with 6 sigma quality, where I've got that process capability of 2, and I'm able to fit my whole bell in there twice, then this is where I'm starting production. They call that SOP, start of production, or launch, when I'm launching my process. This is typically, usually the best you're ever going to be. I'm running my process with known conditions. I have my one operator that's running it for a day. I've got one set of environmental conditions. I've got one set of raw material lots for all the different bits and pieces that are being produced. I have one setup. I've got one set of procedures I'm doing. It's only experienced one form of maintenance activities. So my bell is as tight as it's usually going to be, unless I make some major changes to the process later on. So what happens is, as I start to run this over life, as I start to get, the line starts to get more experience, my machine starts to break in, I experience temperatures, I get summer, winter, spring, and fall. I've got different operators, different shifts. I get all of these normal causes of variation that happen. So my bell is going to start to wiggle and waggle and move around and get fatter and shift. So some people theorize that it might move plus or minus 1.5 sigmas. I don't know if it's that or more or less, But the point is you have room to de-evolve. You have room if you're starting at that 2.0 level, or even at a 1.67 perspective when you first start, to let it experience life a little bit. If you start out at 1.33, 1 1/3, where you have room for those parts in that fourth sigma spot, if anything starts to shift left or right, you're going to be immediately in a reject making situation. And you don't want to have that happen. So the tighter you can start at first, the more room you have to experience life in the long term. So now let's look at a couple of examples here. This is called a one-sided CPK table or PPM table. And we're going to do 4 examples. And in this case, you look at the CP, let's say my CPK is 0.67. I am going to turn on my little pointer here. So you have the ABC here. So I'm looking at 0.67. So there's the A is the 0, the B is the 0.6. I'm going to go down to 0.6. And then my second decimal here is the 7, 0.6, all the way over to 7, 0.67. If I have a process capability, a CPK of 0.67, that's 22,216 parts per million only on one side. Only on one side. This is a one-sided table. It doesn't assume that your bell is positioned in the middle. So it's just looking at this one side. In this case, since my bell is in the middle, and I'm going to have an equal opportunity on both sides, I could double that, and I would have 44,432 parts per million out of spec. This helps us when we're trying to justify why we need to do an inspection, or why we need to add an equipment, or why we need to make some changes to put a poka-yoke in place. It helps us with our justification. It also helps us understand the risk of what we might putting through to the customers. If you want to actually get to your percentage, you divide that value by 10,000. So let's look at another example. Let's say that I have this process capability of 1.0, like we showed before. If I have this 1.0, excuse me, you already know we're going to have some parts out of spec, because it's going to be 3 parts per 1,000 that are hanging out there. So I've got 1.00. I'm going down to 1.000 is over here. That's 1,350. I've got 1,350 parts per million that are going to be out of spec. And this is really a little bit deceiving. It's not totally intuitive, because you don't see the blue bell hanging outside of the spec lines. And this is where people can get really confused, because they say, wow, it fits in there, therefore everything's good. And it's not. So now you know that that's not good. And this is why your bell needs to be skinnier than the spec lines. So in this case, I'm going to have 1,350 part per million out of spec on the one side. Since my bell is centered, I can multiply that by 2, because I'm going to have that equal opportunity on both sides. So I'm going to have 2,700 ppm out of spec. Most people round that up to 1/3, to 3. But the point is that this is not a good situation if you are making safety products, or you have a safety feature that you need to manage. Let's look at another example. In this example, the bell is shifted like the one we started with. And in here, it's really tight to the one side. So my upper capability is a 1.0, because that 3 sigmas fits in between the average and the spec line one time. And I know I'm going to have that 1.5 per 1,000 out here on the right-hand side. So again, I do that 1.00, and I've got 1,350 parts per million hanging out there. On the left-hand side, because my CPK is 3.0, the table only takes you down to 2. So you're not going to have an estimated amount of risk on the left-hand side. And let's look at one more example. So in this case, I've got the bell centered in the middle. I know that this is a process capability of 2.0, because this whole bell can fit inside the spec range twice. And I've got room for 6 sigmas between the average and the spec line. And in this case, it's considered negligible, or I'm not going to have an issue, if you will, with risk for this product or process. Excuse me. So now let's look at how sigma is calculated. And we're going to do it by hand. If you're taking pictures of these, just wait until I get to the last one and I'll tell you when you can take the picture. This is how the formula looks. The standard deviation is the square root of the sum. That's a big fancy plus sign in Greek. Epsilon is a big plus sign. And I'm dividing it, or I'm doing the average minus each individual reading, and I'm squaring those. So that's the sum of the squares divided by my sample size, which is n minus 1. Now, in this case, just for simplicity and for time, we're only going to do 3 readings. We have a 2, a 1, and a 3. The sample size is 3. My average of those 3 values is 2. So 2 plus 1 is 4 plus 3 is, 3 plus 3 is 6. And then 6 divided by 3 gives me 2. So now we're going to do the old-fashioned plug and chug. I'm going to take my blue 2, my blue average, and I'm going to subtract it from my first 2, my first reading, and I'm going to square that. I'm going to add it to my next item, 2 again, minus my second value, which is a 1, and I'm going to square that. And I'm going to add it to my third one, which is the average of 2, minus the 3, and I'm going to square that. And now I'm going to divide it by my sample size, minus 1, 3 minus 1. And in doing this, this is going to tell me how big my sigma is going to be. So 2 minus 2 is 0. I'll square that. 2 minus 1 is 1. 2 minus 3 is a negative 1. And I'm going to divide that by 3 minus 1, which is 2. Now, keep in mind, you have to use the 3 minus 1 value in here. This 3 minus 1 is considered your degrees of freedom. And actually, you have to have that minus 1 in there. I call that a punishment factor. It makes your sigma fatter. And the reason why you use this n minus 1 version of sigma is because we didn't take every single reading. If you take all of your readings and all of the possible population, then you don't have to use the minus 1. But in every other case, you need to use the minus 1. So make sure you're using the right form, the right formula here, so that you don't get the wrong sigma out, because that'll make you have an incorrect assessment. 0 squared is 0, 1 squared is 1, minus 1 squared is 1, and I'm going to divide that all by 2. So 0 plus 1 is 2 divided by 2. 2 divided by 2 is going to be the square root of 1, and the square root of 1 is 1. That is a hard way to get to 1, but we did it. Here is what the histogram looks like. I have a value of 1, a value of 2, and a value of 3. My standard deviation, my sigma, is 1. So 1 times 3 is 3. So I'm going over 1 sigma, the second sigma, the third sigma. So my average is 2. 2 plus 3 puts me at 5. 2 minus 3 puts me at negative 1. And that's what my distribution would look like. In real life, we would want more than 30 readings in here, 25 to 30 readings in here to make sure we're normally distributed. In this case, we just did this with 3 so that you could see the samples. Imagine if you had 50 readings, 100 readings, 1,000 readings, and you had to do this all the way across that top. Very painful. When I went to college, we did this by hand because we didn't have those fancy calculators, and Minitab wasn't quite doing that then that I know of. Anyway, I still know how to do it by hand, and now so do you. So now what I want you to do is to take a few minutes to actually calculate the CP and CPK upper and lower based on these 4 examples. The formulas are here, and you can do it based on your last name. Just do any one of these examples. And in all cases, the lower spec limit is 0, and the upper spec limit is 10. So the upper spec limit minus the lower spec limit is going to be 10 minus 0. And you're going to divide that by 6 sigmas, 6 times your sigma value. And that will give you your process capability. And then to get your upper capability, your upper CPK, you're going to take your upper spec limit, which is always 10, and you're going to subtract it from the average. In the first 2 cases, the average is 5. In the third case, the average is 7.5. And in the fourth case, the average is back to 5. And then you're going to divide that by half of the bell, or 3 times the sigma that we have posted here. So take a few minutes to get yourself to just do one of these across, and we'll show you the answers and the math. We went through the lower. The lower capability is to take the average, which you have here, the 5s or the 7.5. You're going to subtract it by the lower spec limit, which in this case is 0 in every case. And you're going to divide it by half of the bell, which is 3 times sigma. So here is for the first one. I'm taking 10 minus 0 divided by 6 times 2.5. And that gives me 10 divided by 15, which is 2/3 or 0.67. And the bell fits in here 2/3 of the time. And I know I'm going to have 4.44% nonconforming on 2.22 on each side. And I can go to that table to help me calculate how many units are going to be nonconforming. For the next one, we can do the same math, the same plug and chug. And now my process capability is 1. And you'll notice that the values are the same. The CP is equal to the CPK upper, which is equal to the CPK lower. And that's happening because the process is in the middle. It's centralized. When it's not in the center is when you're going to get differences. So in the third example, we can see that the process capability, the whole bell can fit inside the total width twice, which is great, but it's not centered where we need it to be. If we could shift this guy over to the left, just only 1 standard deviation, that's all we would need. It doesn't have to go totally to the middle. It only has to go over enough to catch those 1.5 parts per thousand. And then in the last one, we see that this fits in here twice, and the CPK upper and the CPK lower are 2.0. If you do have questions as we're going through this, please feel free to put them in the chat, and we will get to them after the end of the session. So now let's talk about how this ties into measurement system analysis, MSA. So when we measure something and we make an assessment, we either get the perfectly correct answer, but we have 2 chances of making a mistake. We have 2 risks. The first risk is an alpha risk, and that means when we put a good part in the trash or we rework a good part, that is where we are saying, whoops, sorry, it's not good, go rework it. But it's really a passing part, and we don't know it. It's unintentional, it's inadvertent. And I always remember the alpha risk as being, oh, darn, I just threw away a good thing, darn. A beta risk is when we actually accept a bad part and we don't know it. And I always remember a beta is, boy, that's bad. That's really bad when we accept a beta. The deck is being made available as a PDF to the conference. So you can get it from them, or if you want, you can get it through my LinkedIn at the end of the session. So when we do measurement analysis, there's 3 general things that we need to watch for to make sure that our measurement system is giving us the right readings. The right readings are accuracy. Accuracy is done when the first bullseye is showing you that this is really accurate and they're clustered together and it's in the right spot. It's giving you the right reading in the middle. In the second one, this is giving me an inaccurate. It's not in the middle, but it's very precise. They're clustered together, so I'm shifted off in my reading. Accurate but imprecise, the average of these readings would be the good value. And in here, I'm all over the board. So accuracy is assessed by calibration, and a lot of us do calibration really well. But calibration isn't the full story. You can have a perfectly calibrated gauge that gives you a very wrong reading. I had an example where we were making a metal plate, and the metal plate had coating on it. And the coating, the plates were coming off a paint line, and it was a heated process. So the metal plates were coming out very hot. The plate was being enameled. The plating was being enameled onto onto the metal surface, and they had a digital gauge, and they would have a little sample coupon. They would put the gauge on the coupon, and it would say, this is X millimeters thick, and then they would put it on the part, and then they would get a reading. And they didn't know it at the time, but the readings were 100% wrong. And what was happening was because the metal was being heated up to such a high temperature, the gauge wasn't properly performing for the measurement of the paint thickness, because the magnetic indicator was being all messed up due to the temperature and the electrical interference that was going on there. So calibration does not enable you to always get a correct reading. You must do a check for precision, which is what gauge R&R does for us. This gauge R&R helps us determine how much error we have in our gauge system. We are allowed globally to have at least 10% gauge error. When we're measuring critical and important things, we want to have less than 10% error in our gauging systems. The last thing we want to look at is what we call resolution, or how well we can discriminate the readings on our device. So my device here, my clock says it's 10, 10, 35, plus or minus a second. Okay. If I take the second hand off, I can no longer discriminate or read times to the seconds. It's gone. Now I can say it's 10, 10, plus or minus a minute. So is it 10:09 or 10:11? Now, if I take the minute hand off, all I can do is say it's 10:00 something. Is it closer to 9 o'clock, 10 o'clock, or 11 o'clock? And I've lost a lot of my ability to discriminate. So in resolution, how well can we read the gauge? Gauge resolution needs to be at least 10% of the tolerance. For example, a speck of 0 plus or minus 10 needs to read to at least plus or minus 1. So all these three things, I look at these as a three-legged stool. These all need to be in play so that your readings come out accurately. So now what does resolution do for us? When we look at our gauge processing here, we can see that our process capability here is 1.0. This process fits in our spec lines one time. Yay us. But now we know that we're going to have 3 parts per thousand out of spec. Our process is going to be giving us out of spec parts, just due to how it's being produced right now. If I have a gauge with 10% error and I read a 10, my gauge reads a 10, it really could be a 9, or it could be an 11. 1/3 of the time, I could be making an error here. I could be making a beta error where I'm actually passing a bad part and I don't know it. It's reading a 10, but it could be an 11 just due to the gauging error in itself. I know my process is going to be making parts this big, plus my process is going to be also making out of spec parts. Because of this 10% gauge error, which you're allowed to have, if this process capability is so big, like it is, you're guaranteed to ship and send out of spec parts when you think they're actually in spec. Now, this happens whether it's a human doing the gauging or even if it's an automated or a virtual electronic gauge. Mechanical, electronic, automated gauges have the same opportunity to have gauge error as humans do. So keep in mind, it doesn't matter what the gauging system is, they all have some level of error going on. If I read an 11, I'm going to throw away or rework that part. However, the part could have been a 10 or it could have been a 12. 1/3 of the time, I'm going to throw away or discard or rework a good part. And that's not good for me either. So I want to make sure that when I start out that my process is skinny enough so that I cannot make these errors. So with a more capable process when you're starting out, I'm still going to have a 10% gauge no matter what you do. Now, some people can get their gauge errors less, and that maybe allows you a little bit more room to play. But the point is that sometimes I see a lot of gauge errors more than 10%, and that gives you no wiggle room at all. So now if in this case, if I got a reading of 6, okay, my part could be a 5, could be a 7. I cannot make an alpha error or a beta error here. I can't throw away a bad part. I can't accept a bad part. In both conditions, I'm protected as a company and my customer is protected as well. And this is why this is why you have a minimum process capability of 1.67 or 1.33 for safety features when you first start out, because it allows you to account for that gauge error that's in your system. Now, gauge R&R is needed everywhere. We need to do this everywhere we go. When I see a lot of engineering test laboratories, you go into the test lab and they say, oh, they're all calibrated. Oh, I have great calibration records. Well, have you done a gauge R&R? And they say, no, we don't need to. We're a gauge lab. We don't make product. And the reason why it's even more critical in an engineering test lab is because they're not making hundreds and thousands of parts. They're making prototypes, 1, 5, 10. And if their readings are not accurate and precise, they're going to be making a whole lot of build assumptions and build specification criteria off of incorrect readings. So you really need to make sure that your upstream engineering testing process, your quality testing process, your laboratories, your suppliers, your maintenance teams, your maintenance guys, they're running and crawling all over your machines. They're using handheld micrometers, calipers, maybe laser mics. Maybe they're even using a good old-fashioned tape measure. And they're setting up your machining and equipment, and they're setting lasers and doing all of this stuff. And they're only doing 1 or 2 readings also. What if they get it wrong? What if their reading isn't accurate? So all of these different places and spaces need gauge R&R to be performed, not just the production line. So what we've done is we've had a rapid, high-level overview of how PPK and CPK generally work. Hopefully you practiced and were able to get through the formulas. And then we connected that process capability to the tolerance, to the gauge percent tolerance of error, so that you could see the effect on alpha and beta errors. Now you guys now have a superpower. You understand that your bell, your distribution is going to have parts hanging outside of it. And people need to remember that they're kind of invisible. You really don't see them, but they're out there. You need to know that when you have a gauge reading, that it might not be that exact value. It could be a little less, it could be a little more, depending on the amount of error that's in your gauging system. It might not be just a human error. It can be an automated electronic gauging error. So that's what we've been able to go through. I want to be able to open this up for questions. We have about 7 minutes before Ellen cuts me off. If you have any questions, if you want any more details or information, please feel free to join me on LinkedIn. I'm the only JD Marhevko that's out there. And we can open this up for questions, Ellen.
Thanks, JD. We have a couple of questions that have come in the chat. And again, a reminder, if you want to ask a question to JD, please put it right in the chat. Couple of questions were asking whether or not they could have copies of your slides. If that's possible, JD, we can always post them on the conference
Yeah,
website.
I've given you the deck so you
Okay.
can put it on as a PDF. Yeah.
Okay, thank you. I will take care of that. The other question is, it comes from, what is your thinking about the Wheeler method for evaluating the measurement process? JMP has been promoting it, and now Minitab has the capability also. Adding up standard deviations in the traditional MSA has been always seemed sketchy to me. That was the question.
I'm not going to give my personal opinions because it's pretty political. I do find that there's lots of different approaches, and they're all directionally correct. The point is how much error do you have in your system? Whichever way you go about it, generally your customers dictate that methodology to you. And you need to use the formats that they require. And different customers require different formats. I find value in most of them, by the way. So I do them all across the board.
Thanks. Okay, I'm looking. Do you have more information about doing GRR in RD engineering labs? Oh, sorry, this thing is moving around. Hold on. Without specification limits or tests. Sorry. Do you have more
Um,
information about doing GRR in RD engineering labs without specification limits or tests?
So when you're doing a gauge R&R, it's both repeatability and reproducibility. So you can do for the instrument itself and its ability to repeat or replicate those same readings over and over and over again. That's a helpful test and technique that can be done. In real life, when I am in a laboratory and I'm making a prototype or a part or I'm sampling something, I generally have a range in mind of how that part or process is supposed to function. So I would apply those general guidelines as a way to say, can this gauging system measure that accurately? Because at some point in time, it's going to go to the floor or go to the production environment, and then they're going to be measuring it out there. So if you don't have specs yet, put some out there that are generally or directionally correct, or you just go for the full the total ability for replication.
Okay, thanks. There's a question here. I'm not sure I understand it. It says, can you give advice to our process as we do so many one-off items?
Sure. With a one-off item, we would call that maybe a short run. And in that case, you're going to have families of products, or you're going to be looking for the variation of the process itself. It's pretty common. That happens in a lot of machine shops. So you want to make sure that your gauging results can function in the environment that you're running the process in. So you just take your different one-offs. You're going to have some general framing, not bigger than this, not smaller than that, and that's what you use as your guidance.
Oh, thanks, JD. We have 5 minutes left. Did you want to take one more question or did you want to?
Sure.
Okay, we have one more. Should we use GRR for ongoing monitoring and measurement for production after design has been completed or outside of design changes?
That's an excellent question. In the IATF guidelines, they like to see that you repeat your gauge R&R studies on a regular frequency. Kind of like you calibrate on a regular frequency. Once that's been proven, then it's a matter of gauge function. Is the gauge working properly or not? Do I have a battery issue? Do I have a worn out condition issue? I typically rerun gauge studies when any of the conditions of the process change. If I get a new operator, I might do a gauge study to calibrate that operator to make sure that they can run well. If I move my process to another location in the facility, I've got new lighting, I've got new ambient conditions, I'll do it then. If I'm doing a new supplier, I might do it because I might have some kind of sensitivity to my supplier raw materials coming in. If I change my machine type, going from machine A to machine B, it's you do that general Ishikawa diagram of what are the types of changes that could happen that could affect your gauge study and the amount of error that it has. I do show that in another session that I hold on actual gauging systems.
Thank you, JD. You were actually fantastic. We love it. And again, if anyone has any questions, please contact JD directly. And thank you for attending today. This was very informative. And JD, you're always wonderful. We thank you very
Oh,
much.
thank you so much. I appreciate all of you being here. Thank you so much, everybody. Have a great conference. Lots going on. Thank you, Ellen.
Thank you.